Okay, so I hope I'm audible, and so let's get started. I welcome the viewers to this problem solving and live interaction session for the subject experimental stress analysis. Today we will be discussing the contents of week 8, which has to do with photoelastic coatings. My name is Ganesh Ramaswamy. I'm a PhD scholar in the Department of Applied Mechanics and Biomedical Engineering, working under the guidance of Professor K. Ramesh and co-guidance of Professor U. Saravanan from the Civil Engineering Department at IIT Madras. So with that, let me move on to the first question. So the first question says the ratio of the strain coefficient K, from this is visible. The question says the ratio of strain coefficient K, ratio of the strain coefficient K to Young's modulus E for four photoelastic coatings follow the relation A greater than B greater than C greater than D. Out of the four coatings, which one would be an ideal choice for reflective photoelastic analysis is what we have been asked. So what we are essentially trying to see here is we have the strain coefficient K, we have the strain coefficient K divided by E of the coating. So this is the ratio, and it is given that R of A is greater than B, greater than C, greater than D. So the issue with photoelastic coating, basically, let me just go through a brief of how these photoelastic coatings work. So in transmission photoelasticity, we saw that once we have the light source, the light gets transmitted through the specimen onto the front analyzer, and that is what we try to analyze. Whereas the situation is a little different in the case of photoelastic coatings. So let us say that this is loaded with some loads, and let this be the prototype, meaning it need not be birefringent or transparent for that matter, need not be transparent. So what we essentially do here is we take a coating material, we coat this with a material. Let me reduce the thickness. Yeah, we coat this surface with a material that is photoelastic. This is the photoelastic coating. Yeah, so this material is a photoelastic coating. So essentially, whatever we were doing on one side, meaning we used to have the light source, excuse me. Hello. Yeah, you call me after reaching the gate. Okay. Yeah. So we used to have a polarizer, or rather, we had the polarizer like that, and then we have the analyzer and quarter wave plate like that. We had the specimen here. So we used to have it like this. Basically, in transmission photoelasticity, in the and transmission photoelasticity. This was the setup. Because this was transparent. However, in the case of reflection photoelasticity, what I'll do, I'll just reduce the size of this. In the case of reflection photoelasticity, we basically try to have the light source here, have the elements like that. This impinges on the surface and it reflects back. And then we have the eye or the camera. I'll just say observer in whatever form that is. So essentially, this is to do with surface stresses or strains actually. Rather, it should be surface strains. Surface strains from the specimen get transferred to the coating. And we assume that the strain compatibility between the coating, the bottom surface of the coating and the top surface or the surface of the specimen, it has a strain variation that is holding, it is compatible. So that is the basic tenet with which we have developed the photoelastic coating techniques, and it holds when we paste it properly. It will hold and faithfully transfer it. So essentially, we will be having the light source that impinges here and then goes back, and this is the observer, and this is the observer here. So since we are trying to study the surface strains, it is essential that the coating participates as less as possible in the load sharing, or rather, the coating does not reinforce the specimen. Now, if it so happens that this coating has now if this coating is having a strength that is higher than the prototype itself, it will start providing reinforcement to that. And when we apply the loads, this participates in the load sharing in a much more dominant fashion, such that so we are no longer studying the mechanics that we are trying to study of this prototype, but rather the coating is also playing a part in it. That is why, and essentially that is driven by the elastic properties. So that is why when we have a prototype, we try to go for a specimen that provides the least reinforcement possible, and that can be gauged readily by the Young's modulus. So what we want is EC to be less. EC less means less reinforcement. So this implies that R must be more. And we can see from here, out of these four, we can see that R is maximum for A. Hence, we will go with the coating A. So I hope that is clear. So let us move on to this question. Consider the table given below. So we have been given the material, the name of the material label as an A, B, C, D. And then we have the name of the material, namely polycarbonate, polyester, PS3, and polyurethane. The Young's moduli of these materials are given here, and the strain coefficients are given. One needs to perform a reflection photoelastic analysis on silicon rubber specimen. So the specimen here is silicon rubber, which has a Young's modulus of, this is for the specimen. So this has a Young's modulus of 0.05 GPa. And it has been asked what is the ideal choice for the coating. And we have been given these properties E for A. So EA here is 2.21. Yeah. So and EB is 3.86. EC is 0.21 and ED is 0.004. Similarly, K has been given. So if I were to take the ratio of strain coefficient by the Young's modulus, so this will come out to be RA. Let me just add a column here, R, which is equal to the strain coefficient by the Young's modulus. So let us evaluate these values. If I were to evaluate, this comes at 3.16 by 2.21, 0.07, or 0.04 by 3.86, 0.01, and then this is 0.02 by 0.21, 0.02, 0.21. So this is 0.095 and this is 2. So we can see here again that R maximum, R for D, is the maximum. What this implies is this gives the least stiffness, that is the least reinforcement. This ratio gives us a measure of the least reinforcement and maximum photoelastic response. So we don't want it to provide any reinforcement to the specimen. Hence, its stiffness should be very less as compared to our specimen material. At the same time, it should also have a good photoelastic response for us to have at least discernible fringes for our analysis. So, accounting for both those characteristics, if we see, polyurethane suits this purpose the best. So, the ideal choice would be to go with polyurethane for this case. Again, it depends on the specimen that we are trying to analyze. I hope that is clear. And here again, if we see the stiffness of this is one order of magnitude less than the stiffness of our silicone rubber. So it happens to be the ideal choice. So let us look at this question. Best practice to handle stress concentration regions using photoelastic coating is which of the following? So what we are trying to study here is the stress concentration regions. And this we have to do using photoelastic coatings. Now, what do we know about stress concentration regions? Is that in the case in any problem, these areas reach the peak load first. So essentially, if we were to use a very thin coating, now we know that the fringe order that is developed is inversely proportional to the thickness of the coating. And we'll also see some brief derivations later. But the fringe order developed is inversely proportional to the coating. So therefore, if Hc is more, I'm sorry, this is directly proportional. What I meant to say is, if we take sigma 1 minus sigma 2, from our knowledge of transmission photoelasticity, we have Nf sigma by H. So therefore, N is directly proportional to H for other parameters remaining fixed, which means that the thicker the coating, the more number of fringes we will be able to get. This implies that thicker coatings give more fringes for the same load. Now, this is from our knowledge of transmission photoelasticity. Coming to reflection photoelasticity, we also have in reflection photoelasticity the problem of reinforcement, coating reinforcement is a problem. So, the thicker the coating, the more it will reinforce the actual specimen, and our results will start deviating from the actual mechanics of the problem that we are trying to study. So, we have to, so I should say reinforcement is also directly proportional to the thickness. And reinforcement is something that we do not want. So in order to hit a middle ground between these, we have to look for some other via media to go about addressing such problems with stress concentrations. So what we initially do is for the stress concentration region, we can initially coat a thicker, rather I shouldn't say stress concentration region, I should say first the specimen. For the specimen being loaded, initially I'll apply a thick coating, and this helps me identify the stress concentration regions. Once that is identified, once the stress concentration regions are identified, I can go ahead, remove the coating and then use a thinner coating there. Use thinner coating and carry out the analysis. thereby reducing reinforcement effects. Here it is only a qualitative identification. It is similar to our brittle coatings that we will discuss in maybe next week or week after next, where we generally coat the specimen and then where would the coating initially fail? It will fail at the regions of stress concentration because there the stresses will reach the peak. The strains will get delivered to the coating breaks. So that is where the failure initially precipitates, and then it carries on to other regions. So in a similar vein, what we do to qualitatively identify these stress concentration zones, we apply it with a thick coating, followed by stripping that off. And once those are identified, we can use thin coatings in order to carry out our analysis. So let us look at the options. It says apply a thick coating first to identify the stress concentration. Now paste a thin coating over the thick coating. Now paste a thin coating over the thick coating in order to analyze the region of interest. That is one. Apply a thin coating first to identify the stress concentration regions. Remove the thin coating and apply thick. And then apply thick first, remove the thick and apply the thin. So this is the actual answer. Apply thin and then you put thin over the thick. Essentially, it is made of the same material, irrespective of the coating is the same material. So thin plus thick only gives a greater thickness, which provides more reinforcement, which is something we want to avoid in the first place. So naturally, once we identify the regions, we have to remove the coating, do the preparation, and again apply the thin coating and carry out the test. Okay, so I hope this is clear. So let us look at this question. The figure below shows fringes observed in a photoelastic coating test conducted on a bolted base of a lamppost. So we have a lamppost here. This is a lamppost. And then we have the bolted base. We have the anchor bolt here. And we have they have tightened it with screws. So they have applied the. So we were looking at this question. Figure below shows the fringes observed in a photoelastic coating test conducted on the bolted base of a lamppost. The isochromatic fringes qualitatively show the presence of which of the following stresses? That's what is asked. So essentially, what has happened here is during the tightening process, the stresses have developed, which is basically the assemblage of the component. And there is essentially no way to model this because this is dependent on the workmanship that is taking place at the site. So although it may be conceptually appealing for us to include these stresses in our analysis, there is no way for us to gauge, which is why we will take a buffer of this much is the allowable deviation, and perhaps we in the good for construction drawings or uh, the preparation assembly schedule, there we will mention that this is the level of load that needs to be applied or torque that needs to be applied to the bolts, no more, no less, which can be checked. So that is how we have to address this. And this happens to be the technique which can actually measure the assembly stresses. So these are the assembly stresses. Residual stresses are generally introduced due to some imperfections or perhaps misfits, things like that. thermal stresses, we are able to see that we have applied this on the coating, on the external surface of that. So essentially, in the bolt being the same material, due to thermal variation, there cannot be surface, there cannot be thermal stresses actually present. Thermal strains can be present, but thermal stresses generally wouldn't be present. And we are, this is a fixed structure, so there is no, uh, it's not under fatigue loading unless this lamppost is moving, and nothing like that is given. So we can take it that it is not that. Essentially, these are assembly stresses. Similar example is also shown, is also discussed in the lecture for one case where the professor has a handheld polariscope, which is the reflection polariscope essentially. When we saw here, this entire gadget is made small and confined into a handheld device. And one can observe, intense the light and observe the fringes using that, which is widely used in the aircraft industry also in order to measure the stresses and the components essentially, in order to analyze the components. Okay, so let us look at this question. It says which of the following statements are true regarding the correction factor for bending of plates. The first option says correction factors are applicable for thin or medium thick plates in regions of uniform stress. For the restricted case of pure bending loads, the correction factor may also be applied to thick plates. Correction factors are applicable even in the presence of geometrical discontinuities such as holes or a series of holes. And these are not applicable when the plates have an abrupt change in the thickness. When there is no Poisson's ratio mismatch between the specimen and the coating, the correction factor for bending is equal to the correction factor for bending of plates. So essentially, what are these correction factors? These are the introduced to account for reinforcing effects of the coating. Now, how we go about doing this is the correction factor for any problem is evaluated by analyzing the problem with and without the coating and comparing the result. So the ratio of with coating to without coating will give us a factor which will account for the reinforcement effect that is brought about by the coating. So we just need to account for that in our stresses in order to, because our intention is to analyze the stresses in the uncoated material. But without the coating, we will not be able to do photoelasticity on it. So that is why we look for a middle ground, and this is evaluated based on comparing uncoated and coated response. Uncoated and coated response of the structure. So just I'll go a bit aside to discuss essentially what we are trying to do in this case. Let me just see here. So let us say for a plane stress condition, I mean, this explanation will also help in the subsequent sections. So that is why I prefer to go at it a little detail. Let us say that we are assuming a plane stress condition. So for a coating, now we know that from Hooke's law, we know that strains can be expressed in terms of stresses from Hooke's law, from the generalized Hooke's law actually. Let us say that there are stresses in two directions only, so only planar stresses. So essentially, epsilon in direction 1 can be given as sigma in direction 1 by E1 minus nu of sigma, uh, this should be by E minus nu sigma 2 by E. Similarly, we also have the other strain. Essentially, we just need to replace the index. So this will be epsilon 2 is by epsilon 1. Now, in the case of a coating, in order to differentiate, what we will do is we'll take mu to be mu c and E to be EC. EC, or let me put it here, mu c and EC. So in a coating, if I see epsilon 1c in the coating is nothing but sigma 1c by EC minus mu c sigma 2c by EC. Similarly, epsilon 2c is nothing but sigma 2c by EC minus mu c sigma 1c by EC. So far, so good. Now from here, if I were to calculate the difference in the stresses, epsilon 1c minus epsilon 2c, if I do, this gives me epsilon 1c by EC. Essentially, I can take EC common on the bottom. So this gives me sigma 1c minus mu c sigma 2c plus sigma 1c plus mu c sigma 1c. So from here, it follows that I have epsilon 1c to c is nothing but, if I take sigma 1 common, and if I take this as minus, so this will be minus sigma 2c, and these two minuses are there, so everything inside the bracket will be positive epsilon c. So this gives me, epsilon 1c minus epsilon 2c is 1 plus mu c by ec into sigma 1c minus sigma 2c. Now this is somewhat familiar to us, that principal strain difference and principal stress difference are related here. Now we know from our knowledge of transmission photoelasticity, we know that sigma 1 minus sigma 2 is m f sigma by h, where h is the thickness of the specimen. So in the case of coating, I'll apply the same, I'll extrapolate the same concept. So for the coating, I get epsilon 1 c. Essentially, I am taking the principal strain difference is nothing but 1 plus mu c by EC into n f sigma by h. Now, this can also be, this is from the stress optic law. This is from the stress optic law. Now, similarly, if you were to write the strain optic law, essentially we are trying to link the optical response to the strains instead of the stresses. So here we have epsilon 1 minus epsilon 2 is n. Instead of f sigma, we'll just put f epsilon by h. So we have this. So if we just substitute this here, we get nothing but f epsilon is nothing but 1 plus mu c by ec into f sigma. So when we go about doing an experiment, what we can initially do is we can stress the coating material itself, find its f sigma, and based on its material parameter, we can easily relate it to the strain coefficient. Instead of the material stress fringe value, we can get the material strain fringe value easily. So, having said that, the fundamental assumption in the case of assumption in reflection photoelasticity is that the strains are compatible, meaning at the interface, at the junction of coating and specimen, strains are identical or compatible, or howsoever we call it. There is strain compatibility there, which means the adhesive is holding. So, from earlier discussion, we saw that epsilon 1. See, we already have it here. I'll just take it from there. Essentially, yeah, these I have for the coating. A similar thing can be derived also for the specimen. If I were to replace all the superscripts with S instead, actually it would be easier for me to write it afresh. Yeah, for this is for the this is for the coating. For the specimen, it will be epsilon 1 S is sigma 1 S by ES minus mu S sigma 2 S by ES. Similarly, epsilon 2 S is by ES. Now, having got this, we say that the adhesive between the coating and the specimen faithfully transmits the load, transmits strains. Load is transmitted in the form of strain. So this follows, this gives that epsilon 1 C is nothing but epsilon 1 S and epsilon 2 C is epsilon 2 S. So what we are saying is the strain in the coating is equal to the strain in the specimen. So now the strain in the coating we know is, if I were to expand this, I just get, what I get is this quantity is equal to this quantity. Parallelly, because I just don't want to keep writing and it will become a little boring, but this background is necessary for us to understand the things clearly from first principles. That is why I'm delving into it. So I'll just copy paste this for the sake of time. So let us call this equation 1 by matching the maximum principal strain. And this is equation 2 by matching the minimum principal strains, let us say. Now our main intention is to be able to relate, aim is to be able to relate the response to sigma 1s minus sigma 2s, because essentially what we are trying to analyze is what is the principal stress difference in the specimen. That is our main focus, but we have to go through the strain route because we are going for a coating material. So in order to eliminate, I encourage you to work it out later, but for the sake of time and brevity, I'll just uh, take the faster route. In order to eliminate this, what I can do is I can add equation 1 with mu c times equation 2. So what does this give me? It gives me this equation 1 plus mu c times this. So this mu c becomes squared is equal to, I have this plus this quantity. And here one mu c will be there, and then mu s mu c, and this is minus. So I just need to put this here. Yeah. So if I were to rearrange this, on rearranging, basically I will get sigma 1c from here, and then I have this one. So I have 1 minus mu c squared by EC, and then I have sigma 2. I can see that these two quantities cancel out. So this is the left side, and on the right side I have sigma 1s into 1 minus mu c mu s minus sigma 2. So this doesn't subtract out. Okay. So this will be, let us say, plus sigma 2s into mu c minus mu s whole divided by E s. Very well. So this gives me that sigma 1c is nothing but Es by Ec to 1 minus mu c squared into this quantity sigma 1s into 1 minus mu c mu s plus sigma 2s into mu c minus mu s. Now that we have got one, similarly you can eliminate the other, and towards the end sigma 2s also you can eliminate, can be similarly obtained. And what we want towards the end is sigma 1s minus sigma 2s. C can be visually obtained. Sigma 1s minus sigma 2s is what we want. So this will follow that sigma 1s minus sigma 2s is nothing but Es by Ec into 1 plus mu c 1 plus mu s into sigma 1c minus sigma 2c. But it doesn't end here. Why? Because this is not what we will measure. What we will measure is the strain coefficient, and we already have that relation here. How is the stress related to the strain optic coefficient? How is the stress related to the strain coefficient of the specimen? Now, one thing to note here is, okay, I'll come to that anyway. Let me just add one more page here. And this derivation will end soon. I understand that it's going a bit longer, but I'll come to the conclusion very soon. Now, for the coating, right here. For the coating, I know that sigma 1c minus sigma 2c is nothing but n f sigma by t, and f sigma, f epsilon is 1 plus mu c by ec into f sigma. So let me substitute for this. F epsilon is ec f epsilon upon 1 plus mu c. This I substituted here. So I get sigma 1c minus sigma 2c is n ec f epsilon by t, n c t into, yeah, this got mixed up now, 1 plus mu c. Now let me go ahead and substitute this quantity, whatever we have got here, in place of this. So instead of this, I will have this quantity here. So what does this give me? Sigma 1s minus sigma 2s gives me E, EC and EC cancel out, and then these two things cancel out. So this gives me a much simpler expression actually. This gives me ES upon 1 plus mu s, this quantity into the fringe order by thickness into F epsilon. Now F epsilon can be similar to F sigma, which can be represented as lambda by C. F epsilon can be represented as lambda by K. Why this becomes important is this is what is provided by the manufacturer. What they will do is they will apply this coating on a cantilever beam. They will do the after correcting for the reinforcement effects, they will actually calibrate the specimen, calibrate the coating material, and they will specify F epsilon. So it is preferable to replace this with this expression because K will be readily given. So with that, I'll just come to the close of this derivation. Sigma 1s minus sigma 2s, which is what we are trying to study, will be epsilon s upon 1 plus mu s into n by thickness into lambda by lambda of the light by the strain of the coefficient of the coating. So this is the actual relation that we are trying to see, but this is for an ideal case where reinforcement effects are negligible. But this is not always the case. So what we instead do is we will just take this and apply a correction factor to this. So we do this with a correction factor R for the correction factor, and this depends on the problem in hand. So this happens to be the actual relation that relates the specimen stresses to the optical response that we will observe from the photoelastic coating. Now, one thing needs to be kept in mind here is that when we wrote this equation, from our transmission photoelasticity, we wrote it as sigma 1 minus sigma 2 into ns sigma by t. For the coating, we wrote the same thing. One thing to be noted here is when we have the surface like this and the coating like that, we have the light enter here and then get reflected here. So this, if you remember, this H is how it came to be the thickness of the specimen is because we derived it from the refractive index, where for the birefringence, there are two refractive indices. Essentially, they have to cover a distance H, so they will have different velocities. So this happens to be in transmission photoelasticity, we call this the thickness of the specimen because that is what it is. The actual, if you see from first principles, what this denotes is the actual length of the light path that the light has traversed in the photoelastic medium. So here it comes this way and then goes back like that. Essentially, here it comes this way and then goes back like that. Ideally, we should be accounting for this angle also, but this angle we keep it to a minimum and assume this to be normal incidence. So in such a case, the light that enters here, it leaves that way. So essentially what we see is light is actually traversing twice the thickness of the coating, which is why this H can either be understood as the actual light path, this T can be understood as the actual light path. Okay, I think somewhere down the derivation H became T, but anyway, when I post it, I'll correct it. But essentially what we are trying to say is this will be twice the specimen thickness. This is twice the coating thickness, sorry, coating thickness, and that is not free of any error. That is under the assumption of normal incidence. This is twice under the assumption of normal incidence. Normal light incidence on the coating. But that is not so wrong because the angle of oblique is kept very less essentially. So this follows. Very good. So now with this background, I apologize, I digressed a bit, but this background is essential for understanding the thing. So that this is where the correction factors come in, is what I'm trying to say. This is where we try to bring in the correction factors. So if we are trying a uniaxial specimen, let us say, a uniaxial case. So first we will try to analyze what the stress distribution would have been without the coating. And then we'll do the same with the coating where the coating participates in load sharing. And we will arrive at this. Essentially, in the lecture, if you see, these are given, these have been published results by, I think, Zanman and group. So depending on the problem in hand, we can apply these correction factors. So the question asks, which of the following statements are true regarding the correction factor for the bending of plates? Correction factors are applicable to thin and medium thick plates in the regions of uniform stress. Yes, this is applicable. This is applicable. For the restricted case of pure bending, the correction factor may also be applied to thick plates. Yes. The correction factors are applicable even in the presence of geometrical discontinuities such as holes or a series of holes. Here, essentially, this leads to stress jump, stress concentration, or a jump. Hence, we will not be applying this correction factors to any place which has jumps. So, this is not applicable. Correction factors are not applicable when the plates have an abrupt change in the thickness. Whatever leads to a stress concentration, we do not, essentially, we are not trying to analyze them using the correction factors because those have been derived for simpler cases only. So correction factors are not applicable for these cases. Some other way workaround needs to be done. When there is Poisson's ratio mismatch between the specimen, when there is no Poisson's ratio mismatch between the specimen and the coating, the correction factor for the bending is equal to correction factor for the bending of plates. Now, this actually is more to do with plate theory. If we see how the plate theory gets derived, is in general for the bending stiffness, if we see E by 12 EI cube by L, 12 EI by L cube. So, essentially, if we see only planar response, it will be a function of only E. Whereas when we take the two-dimensional response, because it will have bending in this direction as well as that direction, actually the stiffness of plates will come with an additional 1 plus mu square, or there will be a Poisson's ratio term that will be floating around in case of plates. If you have taken any course on theory of plates, you will know that that happens to be the main dividing factor between beam analysis and plate analysis. Because in plate stiffness, essentially a term of Poisson's ratio, 1 minus or plus, I forget, but that Poisson's ratio term will essentially appear. So in this question, what it is asking, if there is no Poisson's ratio mismatch between the specimen and the coating, then this can be extended to that. If you see the correction factors given in the lecture, you can see that this is true. So uh, we can consider this in case of whatever we get the correction factor as in the case of bending can be extrapolated to the same thing under bending of plates also. Yes, sir. Yeah, yeah, I'm sorry. Yes, it is not applicable. Since it is not applicable, the statement is true. Yeah, thank you for that. So I hope this is clear. Should there be any questions, follow-up questions, you please feel free to ask. In the meantime, yeah, yes, sir. Yeah, okay, yes. Yeah, that is why yeah, it is better to relate it to the length of the light path, then there won't be a confusion. Yeah, yeah, yeah. Because what happens is for a coating material, let us say that the manufacturer has already provided K, then there is no reason to do all this. But in case that is not provided, then we may as well take it, pull it using a transmission photoelastic experiment and evaluate, and using the power of this relation which we had somewhere. Yeah, this relation we can back calculate. That is the basic technique. Yeah. Okay, so let us move on to the next question. Okay, so this question asks, on a 30 thick mild steel specimen. So we have, I'll just draw a mild steel specimen, which is, this is 30 thick, and this is mild steel. Having a Young's modulus, ES is 210 GPa. Okay, the a photoelastic coating of 8 is applied. So I have a coating. Let's put it in some different color. And this is 8 It's about right. So this is the coating, 8 The coating is made of polycarbonate having a Young's modulus of EC is 3 GPa. The coating is subjected to bending. Okay, so it is actually subjected to bending. The bending can be either tension or compression. I'm just taking it to be like this. Find the position of the neutral axis of the coated specimen measured from the top surface of the. So essentially, what will happen is when we have this is just similar, very very similar to what we do in composite beam analysis. I suppose you remember that. Essentially, if it is homogeneous and if it is subjected to pure bending, we will have this as h by 2. If let us say this is h, if this is hs, then this will be hs by 2 because by tension equal to compression, it will pass through the centroid. So essentially, for a prismatic member, it will be at half. Uh, so this is for the case of a uncoated specimen. Now what we say is we have coated this. So essentially, we have provided asymmetrical stiffness. So because of this bending, this response will essentially pull the neutral axis above a little bit because there is stiffness accumulation on one side. So the neutral axis gets pulled a bit. So what they are trying to ask is find the position of the neutral axis measured from the top of the tension specimen. So if this was 15 at 15 by 2, it got pulled a little. So what is the new position is what is being asked. Essentially, you can do this by composite beam analysis, but already I have spent a lot of time on deriving things, so I just don't want to keep deriving throughout the class. So I'll just take that expression at face value, and it can be easily derived by our balance of forces and moments on a uh, coated and uncoated specimen, which is the basic principle behind our composite beam analysis. In case you have some questions there, yeah, you can see the lecture how it is derived. It's pretty straightforward. And if there are further questions, you can ask me later. So this shift, or rather, I should say the new neutral axis position. Let me put it here. Yeah. So the new neutral axis position. Essentially, how this will be derived, I will just mention briefly. So here, how this is derived is this portion is in tension, this is in compression. So this tension and compression creates a couple. So that is the balance of moments. Essentially, tension equal to compression is what gives me this position because it passes through the centroid. In the case of a coated specimen, I have calculated the strains here. I have calculated the strains here. That strain can be converted into a stress, and that stress, because the stress distribution will be like this. Essentially, the stress distribution will be something like that. So the total compression, the total tension, both have to be equated in order for you to find out the new position of the transform section. This you can also do based on considering a rectangle and then increasing the width by the modular ratio, which is basically the ratio of this to this. So we will just scale up the material, consider it to be homogeneous. Once we consider this section to be homogeneous, where this width is the modular ratio m into the actual width, then the actual centroid of this section is the neutral axis. Of the homogeneous section is the neutral axis. So that is how this is derived. So I won't derive this, which is why I gave this explanation. So that comes out to be h specimen by 2 into 1 plus EC by ES. So this is what I meant as the modular ratio into HC by HS, the whole square, divided by 1 plus EC, sorry, this is minus, the same thing. So this is the actual position of the neutral axis from the top fiber. So let us compute this. This is 30 mm by 2 into 1 minus EC by ES here is P by 210, which is 1 by 70. And then HC by HS is 8 by 30, which is 4 by 15. Okay, so this is 1 by 70. EC by EH is 1 by 70 into 4 by 15 the whole square divided by same thing with a plus. So what does this come out to be? 1 by 70 into 4 by 15 squared. 1 plus 1 into 30 by 2. So this comes around 14 point. This comes to around 14.96. Now in the event that this was homogeneous section, where would it have been? It would be at 30 by 2, which is 15. So we can see that the introduction of this coating with a very soft material has only managed to slightly pull it. 0.05 uh, it is barely pulling it, but it has still nonetheless pulled it towards the top, the neutral axis towards the top from 15 mm to 14.96 mm. And essentially, this is what we want because we don't want it to get pulled too much, which would imply that this has a reinforcing effect on this. So the actual stiffness of the transformed section is almost similar to that of the uncoated section, which serves our purpose. So this is the actual neutral axis depth from the top. It is from this surface, from the top of the milestone surface. So I hope that is clear. So let us take a look at this question. For some regions of a fiber reinforced plastic coat need to be studied by photoelastic coating. A coating suitable for the study of non-metallic material is selected, and the calibration of the coating material EC, let me use some other color. E for coating is 0.21 GPa and mu C is 0.4. Is sought to be done by a tension test. Okay, so here we are doing the calibration by a tension test. Essentially, what we discussed earlier, they have not given that manufacturer has not given K, so we will try to do it by ourselves using transmission photoelasticity. It is proposed to use white light to conduct the photoelastic coating test. Wavelength of the light considered is 577 nanometers. The test section of the specimen is 25. So what we have done is we have taken this where this is 25, or rather I should put it here. This is 25 mm. The thickness is 2 mm. Thickness of the coating is 2 mm. And the load that is being applied is 250 Newton. And the fringe order observed is 2.6. So here, essentially, we are again talking about sections that are far away from the loading point. We know that for a tension specimen, the entire fringe order will be common because there is only sigma 1 and sigma 2 is 0 and sigma 1 is constant, doesn't have any spatial variation. So the fringe order observed here is 2.6 is what is given. So what do we have to calculate in the question? Determine the material stress fringe value, the material strain fringe value, and the strain optic coefficient. So let us go about doing that. Now for this problem, sorry, for tension specimen, I shouldn't say specimen here because it has a incorrect connotation because we are actually doing this to calibrate the coating material. For the tension test, let me say that rather, test on coating material. On the coating, I have sigma 1 which is equal to sigma y if I consider this to be x and this to be y. This is y, this is x. So sigma y is nothing but what is the load applied? 250 by 25 into 2 is my cross-sectional area. So what is the stress that is coming? This is 50. So 250 is 5 MPa. And since this is uniaxial case, sigma 2 equal to sigma x equal to 0. So from stress optic law, I have sigma 1 minus sigma 2 equal to n f sigma by t or h. Let me take this to be h. And here it is the light path. And as we had remarked earlier, this will be just one time the thickness because that is the light path actually. So this is 5 minus 0 is n is 2.6 into f sigma is what we are trying to find here, and the thickness is 2 mm. So actually if we were to replace it just with this, we will see that this thickness actually cancels out. But anyway, so this comes to 10 by 2.6, which is f sigma comes out to be 3.85 Newton per mm per fringe. So we have actually managed to find what f sigma is based on the information given. So this comes out to be 3.85 actually. Okay, yeah, 3.85. The material strain fringe value is asked. Now we have that relation. Let me just take that from, yeah. So we have that here. So what does this give me? This gives me 1 plus Poisson's ratio is given to be 0.4. So this is 0.4 by EC. EC is given to be 0.21 E3 because we have to substitute that in consistent units. Since this is Newton per mm, we have to substitute that in MPa into 3.85. So this gives us F epsilon as this upon 0.21 into 10 power 3 into 1.4. So this gives me 0.0256 mm per fringe. That you can also evaluate based on dimensional analysis, although fringe is not any dimension. So we have got this as 0.0256. So this is 0. Okay, they have asked us to report it in this form. So we'll just multiply this by 10 power minus 2. So we'll just multiply this by 2. So this is 2.56. Be 2.56 E minus 2 mm per fringe. Very well. So the strain optic coefficient, as we discussed this also, we discussed somewhere. Yeah. So we saw it here that this is the strain optic coefficient. We have f epsilon and lambda has been given, so we can easily calculate this. So let us go ahead and do that. So the strain optic coefficient K comes out to be lambda by f epsilon. So lambda is 577 nanometers. So this is in meters, and then I'll convert that to mm divided by 0.0256. So what does this come out to be? Into 10 power minus 9 to 10 power 3. So this comes out to be 0. This gives me K equal to 0.0225. So again, this has been asked in this form. So we'll just multiply this by 100. So 2.25. So we have this as 2.25 E minus 2 fringe. This is coming based on our dimension. So not to be confused with what is this weird unit, basically. Because we developed everything from, this is just to tell you that this has, this subsumes the fringe order inside it. That is all. Very well. So, okay. So I take it that this is clear. Should there be any questions, please feel free to ask. In the meantime, I'll move on to this question. Correction factors are important in data interpretation of photoelastic coatings. This is a mere statement of fact, which is very true. They are the functions of the loading, thickness ratios, and also depend on the elastic properties of the coating as well as the specimen materials. Consider that a specimen material is made of aluminum alloy. So we have been given here the, I need not write it again, it's already given here. So for the specimen, I have these properties, and the coating is of epoxy having these properties. Okay, so this is epoxy. Now the correction stress, the correction factor for plane stress loading is as the correction factor for the beam with 25 mm thickness is as the correction for the bending of plate is as. So what they are trying to ask here is, let us say the same aluminum alloy, I subject it to different types of loadings. For example, I take this as a cuboid, actually, let this be thin. Let me connect this. So essentially, let us take a slab and then we'll apply some in-plane stresses, in-plane stress like that. And then if I were to place the same coating over this, that coating will also have some thickness like that. So because of that, what is the reinforcement effect that brings in is what is asked. This again, how will we go about doing that is, we will consider a coating here of some thickness, which will participate in load sharing. So the thickness into its one length will be the area, and that will contain some, that will contribute to some stress distribution, and this portion will contribute to some stress distribution which has to be equal, which will have to be equal to the externally applied load. So with and without the coating we will do, and we will take the ratio to arrive at the correction factor. But conveniently this has already been done for us, so we need not reinvent the wheel. So this is basically in the case of axial loading. In the case of axial loading, so this is evaluated as, I just use this color and I make this red. So the correction factor for the case of axial loading is given as 1 plus hc by hs upon ec by es into 1 plus mu s by 1 plus mu c. I would encourage you to once derive this for your own and to see how this comes about. It's a simple thing to do, but once you do it, at least even if you are not readily handy with the, even if the equations are not with you, you can at least apply first principles and you'll be able to get somewhere. Although this in the exam when they ask, naturally they'll be giving the equations, but I'm just saying besides the point. 1 plus hc. Hc is 3 by 8 into ec is 3.3 by 71. And since I need not convert it into GPA because it's a ratio. So I'll just let that be. And 1 plus mu s. So this is 1.33 by 1.37. So what does this come out to be? 3 by 8 into 3.3 by 71 into 1.33 by 1.37. So this comes to 1.0169, or nearly this is 1.02 correction factor. So what are we seeing from here? If we were to take the ideal case without the correction factor, we will be uh, essentially making an error of 2% in the case of axial. Now this again, as we see, it is a function of what specimen has been taken, what coating has been taken. If these ratios are way off, then naturally we will have a result that is way off. But in this case, the correction factor comes to 1.02 only. So this is 1.02. The correction factor for the beam of 25 mm thickness. Now again, this it's a big formula, so I'll just write it once for bending. In this case, let us say that there was a coating on top. Essentially, there won't be strain variation between the top fiber and the bottom fiber of the coating because it is under uniaxial tension. Whereas in the case of bending, if we see, there is strain variation right from this place, right from the neutral axis, there is strain variation. So there is a difference between, 1 minute, there is strain variation like this. So there is a difference between this and this. So essentially, strain will be varying linearly. So this creates more complication in the case of bending, but that has been solved essentially, and we have one standard expression. So I'll just write that down. It gives me the correction factor in the case of bending as 1 plus Eg, 1 plus Eg by 1 plus G into 4 1 plus Eg cube minus 3 1 minus Eg. Actually, this is not that much interesting because it's just number plugging and number crunching. But in order to make this interesting, I suggested that you once derive this from first principles and see for yourself whether this comes out to be correct or not. Uh, Once we do that, we'll also get some confidence of how to apply and approach these problems. So E is defined as the modular ratio essentially, EC by ES, which is in our case it is 3 by 70 by 3, sorry, 3.3 by 71. And then we have G as HC by HS, which is HC is 3 and that is 8. So this is 3 by 8. And then mu S and mu C, 1 plus mu S, same ratio actually. So I'll just take this, I'll copy this and I'll put it here. So this value is over here. So it is just a matter of substitution. So anyway, let me do that for the sake of completeness. So this is 1 plus 3.3 by 71 into 3 by 8 by 1 plus 3 by 8 into, okay, this is becoming a little unwieldy. So what I'll do is I'll take this into whatever comes in the bracket. This I'll maybe when I post this, I'll write that fully. I won't be doing that now. So E is 3.3 by 71. E and G is 3 by 8. So anyway, what I don't want to solve this now because it's a big calculation. It is simple to do. It is just number plugging. So what I would rather do is I'd rather leave it here and maybe when I post this, I'll post the full solution for the sake of time. So this I'll post. So this will come from this expression. Whatever this gives, we'll get it here. Correction factor for the bending of plates. Okay. So now this is a little bit different. Essentially, when we have plates, or analyzing plates, where the specimen and coating, or rather, I should say, material is different, which is almost always the case. There will be the stiffness factor coming in for the plates as we discussed. So this RF for the case of bending of plates is given as another big expression 1 plus MEG by 1 plus G into 4 1 plus MEG squared minus 3 1 plus MEG squared whole square divided by 1 plus MEG, where E and G have the same definitions except M will now be defined as 1 minus mu s squared upon 1 plus okay, 1 minus mu c squared. So naturally, when we see that these two are same, M goes to M becomes 1 and M just disappears out of this equation. So it waters down to the same equation that we were using earlier. So that is the basic principle behind it. Again, this I will plug the numbers and do the entire calculation and post it because I don't want to be pointlessly doing number crunching here. The essence is the concept needs to be understood well. So in that conceptual explanation, if there are any questions, please feel free to ask now. Anyway, because I've run out of questions now, and I hope you can bear with me posting the sheet with the calculated answers rather than me plugging them right now, because it's just a clerical exercise. So, are there any questions other than that? Okay. Okay. Well, yeah. Yes, sir. Please go ahead. Yeah. Okay. Yeah. 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 Oh, this one you're saying. Here you're saying. Yeah. Yeah. Yes. No, essentially what we have done is we have just replaced the left hand side. by relating this to strain. So that would still, yeah, so that would still hold because we are not touching this at all. Yeah, yeah, yeah. Ah, okay. But the experiment is still for our transmission photoelasticity, right? So this is a theoretical exercise. This what we are relating to stress is just based on our power of Hooke's law. Yeah, yes, yeah, yeah, yeah. As you said, this does not come from the power of reflection photoelasticity. This is just a mere expression that we have written because we are replacing in terms of strings. This is not to be understood. It is not to be extrapolated into our concepts of reflection. That is, reflection photoelasticity starts here. Exactly. So it starts here just to relate a via media. We are doing this. It's just an academic this thing. But in most cases, we will be given K from our this thing. So this might won't be required. But yes, this is a very important point to be kept in mind. Right, right. Thank you. Thank you very much. Yeah, very well. So any other questions other than this? Okay, okay. Okay. Well, if there are no further questions, then perhaps we'll call it a day. And as I promised, I will populate these things properly and I'll post it because I don't want to be doing that clerical work now. So other than that, if there are no conceptual questions, then let us call it a day and we'll meet next week to discuss more on this. And from this photoelastic coating, now we will move on to brittle coating, where many things remain the same, but there are some other nuances that we'll look into. So thank you for attending. Thank you, okay, nice.